Hey all listeners, this is Pradesh Chaudhary Quantum Group. Let's see this very good question of electrodynamics from Krotov. It's a current electricity question. So here there is a network of infinite network of resistor. We have to find the resistance RAB between points A and B of the frame made of thin homogeneous wire. Assuming that the number of successively embedded equilateral triangles with side decreasing by half tend to infinity. Side AB is equal to A and the resistivity of the unit length of the wire is rho. So you can see that this is an equilateral triangle. And within that equilateral triangle, there is another equilateral triangle of the size half. And within that, there is another. Within that, there is another. So the inside equilateral, successive inside equilateral triangle are becoming half in size, and this goes till infinity. So we have to find the resistance between A and B for such situation. Okay. So here is this diagram. So suppose current I enters. Before that, let's assume that the required resistance RAB is say R0. So suppose current I enters at A and leaves from B. So immediately when it enters at A, it has two paths to proceed. So suppose on the two paths that are available to move away, so the currents are split into X and Y. And similarly, the current that will leave at B, from two paths the current will merge and that will become I. And from the path symmetry, this part current would be Y and this part current would be X, like this. And now see that the X current is coming here and X current is going there. So there should not be any part of this current going to this part. So though there is a electrical contact, but the no part of current will go of this wire will go to this part. So you can treat them separately. So I can draw the figure like that. So I have just separated because this current is not getting shared to this part, and the whole current that is going here is passing towards B. So now I am further simplifying this diagram like this. Just I have reduced this thing here, and this point is connected to C. So I'll bring a wire from C to this point, and I'll bring a wire from D to this point, and this is not connected to that because this current is not getting into this part. So now this is, look at this figure first. Here current I enters at A and leaves at B, and then infinitely it getting distributed within the smaller and smaller equilateral triangles. So whatever is happening at A and leaving at B, the same thing is now happening at C and D. So here at the moment it enters at A and leaves at B, so it has to traverse through the infinite this network of letters. Only the size of the successive equilateral triangle is getting smaller. So the starting size of the equilateral triangle is here, suppose that is A. And the same happens here. It enters at C and leaves at D. The only difference here is that at the starting point, the size of this equilateral triangle is the half of the size of the initial equilateral triangle. So because it is going till infinity, so practically there is no difference between this entry and this entry. But the resistance is directly proportional to the length. So if equivalent resistance from A to B is R0, so equivalent resistance from C to D would be R0 by 2. Like for this part, whatever is the resistance, this part the resistance is half. For this part, whatever is the resistance, for this part resistance half, and for each one resistance of the first bigger equilateral triangle, the corresponding resistance in the smaller would be half. So overall equivalent resistance between C and D would be half of that between A and B. So I can write RCD is RAB by 2, and RAB we have assumed to be R0. So that is R0 by 2. Now that is simple thing. So it was given that the resistance of the wire is proportional to its length. Per unit length resistance is rho. So suppose this length, this length, this length, this length, this length are the same, so I assume the resistance of these parts are R, and this is the double of the length, so that is a 2R. And the whole resistance from A to B was R0, and we just propose that should be R0 by 2 then. And the resistance of unit length was rho per unit length, and this length was A. So this part resistance would be rho into A, and that is basically 2R. So 2R is rho into A, so I can write R is equal to rho A by 2. And now I can reduce this to a simple circuit. So this is a 2R here, and this R is here, so that would be R, that would be R, and that would be R0 by 2, and that is 2R. These two series, so that would be 2R. So like this. And these two in turn are in parallel, so their parallel combination will give an R1 R2 upon R1 plus R2, reduce it to get 2R R0 upon 4R plus R0. And now I can just reduce this to this. Now this parallel combination will reduce to this, and this thing and this will in turn be in series. So there, whatever is this resistance, that is the R plus 2R R0 upon 4R plus R0, and that is 2R. So this equivalent would be 2R, this R plus R, and that thing, and simplify that thing. So that will be 4R upon 2R plus R0 upon 4R plus R0, and in parallel there is a 2R. And the equivalent resistance between A and B is R0. So R0 is the parallel combination of this and this. So we can write R0 is equal to parallel combination of this and this, that is R1 R2 upon R1 plus R2, and let's remaining thing are the simplification. So that was R is equal to 4R, that was the upper part, this is the lower part, and just simplify those things. So we are going to get this quadratic equation, and it's a matter of just solving this quadratic equation. You solve that, so we will get R0 is equal to 2R by 3 root 7 minus 1, and 2R was rho into A, so that is a rho A root 7 minus 1 by 3, and that would be our answer. Thank you.